Hello, Flat Earth researchers, debaters and debunkers. Flat Earthers can't think in 3D is the kind of comment you will often hear from globe Earth defenders. The irony is, it's the Flat Earther that's pointing out the three-dimensional nature of perspective that governs all of our observations, whether it's through our eyes or through a camera lens. But the globe Earth defender has to avoid perspective and belittle that idea as much as they can, because perspective is not part of the globe model. In fact, I've always said for the past half a dozen years or so doing Flat Earth videos that perspective is the imaginary curve, or you could say that the mathematics of perspective is the imaginary curve. And this is the mathematics that gives our view of the world depth and dimension. And seeing this is more like an evolution of how our understanding, our collective understanding of the world around us, in the same way that there's been a transition through the history of art that began back before the 14th century with paintings that didn't include perspective. So paintings from the Gothic era or medieval era show us scenes, and they're very intricate, but things are not in proportion because perspective hasn't been included, or the assumption is that it wasn't really worked out at that stage. So there was more evolution to go through as far as humanity's ability to paint realistically. And so in the Renaissance period, the 14th and 15th century, we had artists developing the mathematical formula for perspective and incorporating it into their artwork. And so it indeed does look more realistic because it looks like how we would see the world. So another comment you'll often get is, oh, perspective is just for art. Well, yeah, it's for art because it helps a two-dimensional piece of canvas look like a three-dimensional image. It gives it depth. And again, there is mathematics. So this mathematics for perspective has been converted into this imaginary curve of a globe Earth model. One of the problems, as I said, is that your average globe Earth defender is purely thinking in a two-dimensional format, and one that relates to the way we would illustrate things mathematically with graphs and angles and things like that. And of course, a lot of the observations that we make in the sky are interpreted as being on a globe Earth that's spinning to give us day and night and make the stars and the moon and the sun go across the sky, rather than accepting the Earth as we see it, as a level plane with the sun, the moon and the stars moving across the sky as we see them, and as we intrinsically and instinctively understand them to be doing so, because we know how perspective works. But with the globe we have this ignorance of perspective in place of the globe model. So I'm just going to go through a few different scenarios here, and you can just judge for yourself what you think is more suitable about the way we observe reality. So, number one at the top is a side-on view, an objective view of this scene where we have the chap here looking this way in a horizontal line of sight, looking along this flat, level surface, could be a road with some grass on the side, and we have lights in the sky. The actual heights of the lights is consistent above the level surface, but it really doesn't matter, it's arbitrary, the height of those lights. They could be lampposts or they could be stars, okay? So what the globe Earth defender will do in order to say that it's impossible to get these angles, these viewing angles to stars on a flat Earth, is just stick to this two-dimensional representation, and without any incorporating of perspective, we'll draw these lines like this. I'll just make them go further and further out here, okay, to these distant points. And yes, there will be some changes in angle at which the line of sight must go, but basically you never get to what would be the observer's horizon along this horizontal line of sight here, okay? So you'll get the argument that we would never see this convergence of the surface and the sky if we lived on a flat Earth, because when you illustrate it like this, it doesn't work. We don't get these lines ever coming down to the middle. They just go too far off into infinity to be able to do that. So that's the argument that's presented. Ignoring perspective, because we're talking about someone making an observation. What's funny is what they're telling us, if we go to 1b here now, is that we are experiencing this kind of effect where we see lights in the sky in the distance. The further away they are, the lower to the horizon they get. So they tell us what's happening is that this surface, whether you assume it to be level or curved, is rising up like this. So we've got this surface doing this, it's rolling back. Remember, the globe Earth is spinning on its axis, it's rolling backwards in order to make the stars move. And of course, as time goes by, then the distance between these stars and the Earth is getting diminished really as time goes by, okay? And then the stars hit the horizon. So, you know, the stars are staying where they are, but it's the Earth that's moving. That's what we're being told. And of course, we then get to this point where we're defying gravity. In the real world, if we start doing anything other than being on a level, we certainly know about it. So that's basically what they're assuming we see happening with this side-on view. This is the kind of action that, you know, the Earth comes up to block off the view of the stars. That's essentially what they're telling us is happening. But let's have a look at this same scene here. We've got the same scene as above, but this is, number 2, is a perspective view. So what I'm doing here is illustrating in a side-on illustration what is seen by the bloke, or the chap. Let's change it to the chap. I originally called him the bloke, but I thought chap would be a bit more upper crust. Okay, the chap. All right. So, a couple of things to really think about here about how perspective works is that we have a horizontal line of sight. Okay. Now, if I just look up the words for linear perspective a second, this point here that is illustrated in artwork is called the vanishing point. Okay, it's usually a central point in the image. It could be somewhere else, but it's on a horizontal eye level line, or a line that represents the eye level of the observer. Of course, you are the observer of a painting that's often a first person view. It might be a scene out of a window or something. So the eye level is not exactly your eye level as the person looking at the painting. Nevertheless, what we have is a vanishing point. This is where the surface and the sky appear to converge in our vision. All right, so what I've done is represented it with these red dotted lines here, that we have this declination towards the vanishing point here, and this kind of rising up towards the vanishing point here. Now, a lot of the time we focus on what's happening in the sky, but we've also got to think about the fact that this cone of perspective, if you like, goes up above the observer, but also down below, and really would effectively start underground. So what we have here is perspective is doing its thing, but we have the ground in the way. Now you can see from this that perhaps the higher we go, the further away, the further along this dotted line, this would meet if we actually raised our height. And that's something about how perspective works. Yeah, that's why we can sometimes see a horizon on the surface, but that's not the actual convergence point or the vanishing point of our vision. So what would essentially happen here is that although this is physically like this, and those lights are physically there at a consistent height, the observer actually sees the lights coming down towards the horizon like this. Okay, yeah, and there's increasing, getting increasingly condensed as you get further into the distance. All right, to this point where it all just melds together. The same thing's happening with the ground. Okay, the ground is not transparent. Okay, so we can't see through it like we can see through the sky. So what happens is we still get this road surface here appearing to rise up. Okay, so maybe I can stick some grass and stuff up here. Oops, it's not coming out now. Okay, so these bits of grass, for example, we'll put them here. Okay, they actually appear closer to the horizon. Okay, so this is what's happening in the person's view, in the chap's view. The surface appears to rise up, and the sky appears to go to that vanishing point, which is always the observer's eye level, their horizontal line of sight. Okay, the horizon tells you where you are. All right, and this is the problem with the globe Earth belief, is that they have to have a horizon based on the geometry of tangent lines touching a sphere, given a certain height above the surface. The only difference, as you can see here, that it makes is that your cone of perspective covers a bit more land as you go higher, and this gets wider. Okay, so you just get the condensing later on, further down, or a greater distance. But the horizon will always be your eye level. The horizon is the vanishing point. Okay. So if we now look at this, 2b is the chap's view, his subjective view, as if he's looking at this scene here. So we're now switching it to going into his eyes. And this is, what the Renaissance artists use in a way to try and create their paintings. They would pick a point, it could be in the center, it could be over here. They might have 2 or 3 points as their vanishing points. And you can add other elements like this. You can make a bit more of a grid. Okay, yeah. And this, of course, is done mathematically. There are angles there, and we can then create a scene here which is more like the scene that the chap is seeing through his eyes. Now, for example, we know that if I just did a straight road like that with parallel lines, that this doesn't look right. It looks like a kindergarten drawing. Okay, so we've got to have our road here going off to the vanishing point like that, and kind of following these perspective lines. Okay, and then we have a bit of vegetation on the side there, right? Okay, yeah, so this road here is that road there, yeah, and then we've got these lights in the sky. Well, the ones that are closest to us are going to be up here somewhere, and they're going to follow this path down to the horizon. And likewise on this side, if we've got street lamps on either side, that's what we're going to see. We could even put the lamps in ourselves like that. Okay, there we go, we've got some street lamps. Alright, and this looks like a very crude representation of a scene that you might see. It makes sense because we've incorporated perspective. Yeah? Really, really simple. It's how we see the world. So there's no need to assume that the Earth is doing anything or has any particular shape. We know that when we look across a level surface and we have a parallel sky, we get a vanishing point or a horizon. Yeah? It's the vanishing point that forms part of a linear perspective scheme. Alright? it's the position at which all receding parallel lines meet, basically. So we have what are parallel lines here. There's a parallel line here. Of course, in this illustration, it will never meet. We have parallel lines that are now meeting because we've incorporated perspective, and that's how it would look in the real world. And this relates to number 3, is how distance changes a star's apparent location when you've got more than one viewer. Alright, there's our level surface, and we'll have chap number 1 over here, and he's looking this way, okay? And chap number 1 has a star directly above him, so we're going to call this the ground point. Chap 1 is standing at the ground point of this star, basically where the star is above the Earth. And then chap 2 over here is looking at that star, okay? For this guy, it's vertical. Chap 2, it's going to be illustrated something like this, okay? That's his line of sight to the star, okay? And again, you will say, well, this people defending the globe will say, this doesn't work on a flat Earth, because the further away you get from the star, the lower it gets towards the horizon. Well, again, as we saw just now, that's exactly what happens with perspective when we have parallel lines apparently converging across a level surface. So what actually happens is, because we've gotten further away from this star, it's actually going to appear somewhere like this, much, much lower. And then you would get an angle that is more similar to what we actually see in reality compared to the distance that we travel, whether it's a few thousand nautical miles or whatever. Okay, so this is the reason that a star like Polaris will appear to sink towards the horizon as you get further away, because of perspective. And that works across a level surface, just as we see it, and with stars that are essentially in a parallel line with the level surface. But perspective is what gives us this impression of the stars declining in altitude and getting closer towards the horizon, and eventually getting blocked off by whatever's at the horizon, that limit of our view, our horizon, our vanishing point. Yeah? And that's it, really. You've just got to understand that perspective is the imaginary curve. Thank you very much.